Hello, I'm going to give you some introduction to a technical analysis of variance. This is useful for comparing means of various groups within a sample set, and it's widely used in analyzing experimental data. And the idea is, if you have your data and if you have your predictor is a categorical type data and the response variable is continuous, then the method you want to use is ANOVA. Okay, and so the idea is we want to see if a categorical variable can have any influence on a continuous type variable. Examples, you'll see some examples. And categorical type would be like maybe shape of an object, continuous variable maybe the length or the dimension, and so on. Another example may be accountants versus teachers, who would earn more, salaries. That could be, salary would be a continuous variable, and the predictor variable will be the occupation. Now if we have only two groups, accountants versus teachers, we could use a t-test. But if you have multiple groups, accountants, teachers, engineers versus policemen, and so on, then t-test will not be able to help you much. So that's when we use ANOVA. And for example, if you have three different groups and you want to see if there is any effect on the dependent variable by this independent variable, we could use ANOVA. Okay, and a lot of times clinical trials involve testing different drugs, and these different drugs usually will be compared to a placebo, which will be like a baseline control group, and the others will be called treatment 1, treatment 2. So for the two different drugs you want to test, you would have a placebo, which is simply it's not a drug, it simply looks like a drug, but it's just sugar pill, and we will study the effect of these on patients' health and see how, if there is any difference in for example, average T cell counts in patients after taking these medicines. Another example may be you may have data on different credit cards that people have, and also amount of money they spend on these credit cards, and we could see if there's any correlation between the type of credit card and the amount of money they spend. And the examples used in this presentation is where we want to test if different fertilizers can yield different amount of garlic, and so there are it's done in a farm in Montana. Alright, and so garlic is what the amount of garlic grown is the dependent variable, and the independent variable will be the different types of fertilizers. Now the null hypothesis in the ANOVA analysis is that there is no difference between the means of all the groups. Suppose there are 4 different fertilizers we want to test, and the null hypothesis is that F1 equals F2 equals F3 equals F4. F here represents, I guess, the outcome of amount of garlic grown, and the alternative hypothesis is that one of these equalities don't hold. So we have F1 equals F2 equals F3 equals F4, and one of those and that is one of those equalities. If it does not hold, then that the null hypothesis will be rejected. Now how do we go about doing this? Well, every quantitative variable in your data set kind of varies with respect to the overall mean, and also it varies with respect to the mean inside each group, and also it varies with respect to the mean between groups. So the total variability is basically the sum of variability between groups and variability within the groups. and we need this information to come up with a way of saying the variability between groups somehow affects the total variability more than other part of the equation. Now if we take a simple example of two groups, so we have A and B, two groups, and the overall mean for this data set would be 6, as you can tell, and 3, 4, 5 are the values for A, 7, 8, 9 are the values for B, and the overall mean is 6. Now the sum of squares tells us which is the SST. Okay, so in our equation earlier, SST, total variability means how far apart each observation is from the mean. Overall mean is 6, and each observation, how far away each observation is from 6. We square the distance between each observation and the mean and sum all the squares. That's sum of squares total. So 3 minus 6 squared, 4 minus 6 squared, 5 minus 6 squared, and so on, and we come up with the number 28. Then we come up with what's called error sum of squares. Now error sum of squares will simply, for each group, we want to know how far apart each observation is from the group's mean. So in this case, group A has a mean of 4, and so the difference between 5 and 4, 4 and 4, 3 and 4, we add them together. Similarly, we have group B. We have the mean for group B was 8, and we figure out how each observation in group B is how far away it is from the group mean. We square the differences and we add them all up. So the SSE is 4. Now SSM is the sum of square due to the model. Remember, we are trying to say the group is the reason for differences in overall mean. So the mean for group A is 4, and the mean for group B is 8. So we find out how far away these means are from the overall mean and squares, you take the sum of squares of those. And also, since we have a number of observations in each group, we need to weight the squares by the number of observations. So 3 times 4 minus 6 squared plus 3 times 8 minus 6 squared comes with 24. So 28 equals 4 plus 24, it holds. Now once we have that, then we use what's called means sum of the model over the mean sum for the error, and we calculate F statistic. Okay, and based on this F statistic, then if you have a certain alpha level set up, then you can either reject or not reject the null hypothesis. Now there's one other statistic that is of interest. It's called R squared, which is essentially a ratio of how much of the total variance or how much of the total sum of squares is described or accountable by the model. So it's SSM over SST. Okay, so in our example, SSM is 24 and SST was 28. So 24 over 28 will be the R squared for this example. Okay, and the ANOVA model itself is represented using a mathematical model like this. So dependent variable is always known as Y, and the Y variables I refers to which fertilizer, which group you're talking about, and K represents the index within the group, and the overall yield or bulb weight depends on some kind of a base level, and also depends on some fertilizer, and there is some unaccounted variation, which is the error term. And so we want to kind of tease out this effect of fertilizer on bulb weight. by separating out the base level and the error term. Now SAS does have a good tool for doing this analysis, and once it does it, I can also study the results. Basic assumptions for ANOVA is that observations are independent. In other words, collecting data for one type of fertilizer does not affect the other type of fertilizer. And if in the fertilizer example, if the fertilizers were applied far away from each other, so that one fertilizer does not affect the other fertilizer, we could say that's be independent. And also any error that are variations that are unaccounted for or normally distributed, then kind of will cancel out, and the variances within each group are equal. So these are the assumptions. Alright, now of course we want to make sure these assumptions are valid and supported, and if you have good data collection method, and then you can be assured of the independence assumption, and you can create diagnostic plots to figure out if the assumptions and the error terms are approximately normally distributed. And also we want to make sure the variances are equal across each group. Alright, now how do you go about setting this up? You set up a null hypothesis that all means are equal, and alternative hypothesis at least one mean is different in the group. And we'll start with coming up with some descriptive statistics and verify assumptions, and then do the ANOVA. And ANOVA is where we come up with p-value, and if the p-value is less than alpha that we set up front, then we reject the null hypothesis. Alright, thanks, and we'll see how it's done in SAS. Just a minute.